Hi, it's Sergey from Replica.io, an open source project set on making a breakthrough in designing and implementing distributed protocols for the future of decentralized computing. This talk is about implementation of distributed protocols. It's a companion video to a blog post of the same title. The post discusses the topic in more detail. You'll find a link to the post in the description of this video. I'm gonna share with you some of the observations and conclusions that I made while exploring a number of notable distributed protocol implementations. But first of all, I would like to explain why I decided to do that exploration. I think it would be naive to expect any significant advancement beyond the status quo without first learning from prior attempts to deal with the problem and trying to better understand the typical requirements and difficulties that occur in practice. I also hoped to discover some interesting ideas or techniques that I could use in my project. In the end, I wanted to identify the key areas of focus for the next steps. So I selected 14 code bases written in different programming languages that I thought would be worth looking into. I onboarded myself into one code base after another as if I were to work on them. I tried to understand how the protocols are structured and implemented in those code bases. In particular, I was focused on the general structure of code, node-to-node communication mechanisms, implementation details of the core protocols, as well as mechanisms for monitoring and controlling execution. Here is the full list of the code bases that I have explored. Most of them are written in either Java, Go, or Rust. The last one, Cardano, is written in Haskell. Most of them come from the blockchain area. There are some from the cloud computing, and some are more generally useful. I decided to structure the discussion about implementation of distributed protocols around the following major aspects. The first one, complexity, is about what makes distributed protocols hard to reason about and implement. The second one is correctness, or how to ensure that the implementation guarantees the required properties. The third one is resource utilization, or how to prevent ineffective expenditure of limited computing resources. The next one is maintainability, or how to manage long-running distributed systems and diagnose issues. And the last one is flexibility, or how to achieve high adaptability, reusability, and evolvability of code. We'll begin with complexity. Distributed fault-tolerant protocols are known to be complex and hard to implement, and there are justifiable reasons for that. So there is a certain amount of essential complexity that we simply cannot get rid of without relaxing our requirements. There is, however, another kind of complexity that we incidentally introduce simply because we fail to recognize an easier way to solve the problem. It can start creeping in as early as we try to understand and interpret the specification of the protocol that we need to implement. Then, without having a specific approach to implementing distributed protocols, we would resort to using some universal general purpose techniques supported by the programming language that we choose and commonly used in its ecosystem. Such techniques can be pretty powerful, but using this unrestricted power and flexibility, chances are we'll end up with a code base that is complicated, hard to understand and maintain. When under time pressure, we often start blindly copying approaches from elsewhere, adding temporary workarounds and ad hoc patches, muddling our code even more. Using advanced features and sophisticated techniques can also make the code more difficult to understand. But on the other hand, when used appropriately, it can actually help to make the code more expressive, clear, and easier to understand. Now it's pretty obvious that incidental complexity is bad, but maybe we can simply tolerate it. With rigorous testing, we can convince ourselves that our implementation is correct, but we should remember that complicated implementations are hard to improve, adapt, or reuse later. This way, even a relatively small but necessary change to the protocol can reportedly take months of engineering work. I think we need a structured yet flexible enough approach to implementing distributed protocols that will guide us away from incidental complexity. Let's talk about different things that can contribute to the complexity of protocol implementations and what we can do about that. The first one is modularity. We can solve a complex problem following the divide and conquer principle. We first divide a problem into a number of smaller, simpler problems, then solve them individually, and in the end we combine the solutions back together to address the original problem. Same way we combat complexity in software. A complex piece of software usually consists of a number of components combined together in certain structure. What really matters here is how we divide the problem into pieces, what kind of pieces we get, and how we combine them back together. Modularity can have different levels of granularity. We can have a piece of software that is a complete monolith, or we could divide it into several rather large chunks of code and stop there. That would be coarse modularity, which is certainly better than a complete monolith. But we could continue this decomposition process until we arrive at reasonably small and simple but still non-trivial components, and that would be fine modularity, which is I would argue even better. In all of the code bases that I've explored, there was some level of modularity, but I find that there are still too complicated and hard to follow components there. So I think we need to learn how to achieve fine modularity if we really want to combat complexity. There are different ways how we can decompose components into subcomponents. And the usual way is to focus on the operational aspects, which is how the code will be actually executed. Following this approach, we'll most likely end up with some stateful components reacting to individual external events. But this may not actually help to clearly express the overall protocol logic because in distributed systems, individual events are often causally related in the scope of a larger distributed process, and this approach doesn't express those connections very well. This can also make the code more entangled. Instead, we can focus on the functional and logical aspects by recognizing those implicit logical connections and trying to properly express them in code. We should also organize components in a more structured way. For example, we can arrange them in layers or hierarchically, we can chain them together in kind of pipelines, and so on. Reducing the amount of mutable internal state and making components more static can also help to simplify the code. For example, we can make the consensus-specific components static in terms of consensus configuration and simply recreate them whenever the configuration changes instead of trying to support reconfiguration inside the components directly. Many components require access to some context or environment, such as diagnostic logging or collecting metrics. This is so-called cross-cutting concerns, and we need to have a convenient but clearly defined and restricted way to do that. I think we should by all means avoid fragmentation of the core protocol logic and facilitate local reasoning within the components. Shifting the focus more into the functional and logical aspects can help to achieve that. Even a highly modular implementation isn't necessarily also highly composable. In fact, achieving that property is pretty hard. Composability allows us to easily recombine and reuse individual components. It has huge transformative potential. It can unlock a whole new dimension of possibilities for finding better solutions. In order to achieve composability, our components should be loosely coupled and generic, and we need some kind of unified means of abstraction and combination to put the components together. Most of the explored code bases implement only a specific protocol or a family of protocols rather than trying to address fundamental needs for implementing distributed protocols. What they do for the most part is define abstract interfaces, use various forms of polymorphism and the dependency inversion principle in order to make the components replaceable. But most of those components only make sense within the predefined structure of the implementation. So it's more about decomposing rather than recomposing. There are some good examples of composability that I found in the explored code bases. For instance, in SUI, the network, the communication layer is built on top of Animo, a peer-to-peer networking library based on Tower, which has a composable layered design. In Algorand, the core logic of the consensus protocol is implemented in a kind of composable hierarchical state machine. Concurrency makes achieving composability particularly challenging because the lock-based synchronization primitives traditionally used in concurrent programming suffer from poor composability. There are, however, composable approaches to concurrency, for example, software transactional memory, which is used in Cardano. In general, the functional programming paradigm puts a strong emphasis on composability, and therefore it could be a great source of ideas for enhancing composability. If we want to build future-proof protocol implementations, I think we should approach this proactively and deliberately design for composability. Now let's talk about concurrency, which can significantly contribute to the complexity of protocol implementations. Concurrency is essentially a way to structure code into multiple threads of control or concurrent tasks that can execute concurrently. It requires a more complex mental model compared to sequential programming, and perhaps the main source of complexity in concurrent programming is due to nondeterminism, because the result of concurrent execution may depend on the exact timing of events or execution schedule. Concurrent programming is well known to be error-prone due to such nasty issues as race conditions, deadlocks, resource starvation, and so on. Concurrent tasks that manipulate shared resources require some kind of coordination in order to control concurrency, and there are different ways to do that. For example, we can use lock-based synchronization primitives, or do message passing, or employ software transactional memory. Concurrent threads that communicate through shared mutable memory can suffer from data races, which can occur when one thread modifies a memory location while another thread can concurrently access the same memory location. Preventing data races is not only important because we want to avoid memory corruption, but it can also simplify our mental model. Since concurrent programs that are free of data races enjoy the sequential consistency property, which means that a concurrent execution is equivalent to some sequential interleaving of operations in a linear schedule. And the number of possible execution schedules that can produce different results only depends on the number of non-local operations, which represent interaction between threads or make visible external effects. It's important to note here that the number of possible different execution schedules grows exponentially with the number of non-local operations. Let's have a look at different approaches to concurrency depending on programming languages used in the explored code bases. The traditional mainstream languages such as Java employ a rather low-level approach to concurrency based on operating system threads, shared mutable memory, and lock-based synchronization. In this approach, the code is usually structured into objects exposing thread-safe methods, and they interact with each other by calling those methods. It's a well-known and established approach in the industry, and it's widely supported in those programming languages ecosystems. It provides a pretty high level of control, but it is very tricky and error-prone, and as mentioned before, suffers from poor composability. It's also worth mentioning that operating system threads are relatively expensive, and therefore code bases designed in this approach use a small number of long-running threads, and to execute smaller concurrent tasks they use thread pools. The Go programming language approaches concurrency quite differently. It's based on preemptive multitasking with lightweight user threads called Go routines. It advocates for a message passing style of communication and synchronization, providing built-in support for blocking optionally buffered FIFO channels, and multiple operations on channels can be composed together in a single operation using the built-in select statement. Data races are still possible in Go because there can be unrestricted access to shared mutable data, and it provides rather limited control over the concurrency runtime. Rust emphasizes safety without compromising performance. Its distinguished feature, the ownership model, and a strong type system effectively eliminate data races and prevent accidental sharing of mutable state. As a systems programming language, it supports low-level concurrent programming with operating system threads and shared memory, though the most concurrent code in Rust is written using its asynchronous programming features. Async Rust is a form of cooperative multitasking with passive features that need to be driven by polling in order to make progress. There are different concurrency runtimes available in the Rust ecosystem, and Tokyo is the most widely used one. One can even create specialized runtimes. For example, Sui has a special runtime for simulation testing. Async await syntax provided by Rust helps writing async code pretty close to regular sequential code. Futures can be composed together using different combinators. For example, select, which works similarly to the select statement in Go, or join, which drives a number of futures till completion. It's worth noting that async Rust is in active development. It may still lack some maturity, have limited documentation, and less established best practices. It can also be challenging and sometimes counterintuitive, especially when it comes to cancellation and long-running operations and so on. Despite the memory safety features, its Rust programs are still vulnerable to different types of other concurrency bugs, such as deadlocks, logic errors, and so on. In Haskell, concurrency is also based on lightweight user threads. Haskell allows throwing asynchronous exceptions from one thread to another, for example, to implement cancellation, and handling those asynchronous exceptions safely requires great care in critical sections. There is no explicit support for shared memory because Haskell is a purely functional programming language, so normal communication between threads happens through mvars, synchronizing variables, which can act as synchronized containers for shared state or as one-place channels. There are no data races, but mvars are susceptible to other concurrency bugs. Another concurrency mechanism widely used in the ecosystem is software transactional memory, or STM. It is basically an optimistic concurrency mechanism with atomic transactions over shared mutable variables, or TVARs. STM transactions can be composed safely without exposing implementation details. They can block on arbitrary conditions using the retry primitive, and alternative transactions can be composed together with the or else combinator. Haskell's type system prevents undesired side effects, so rolling back and re-executing STM transactions is absolutely safe. It is also relatively easy and safe to build custom concurrency abstractions and combinators, though there are some limitations of STM. For example, it's not possible to do multi-way communication between threads in a composable manner. There is also no guarantee for fairness between threads waiting blocked in STM transactions. STM incurs some memory and performance costs that depend on the size of transactions, and long-running transactions can suffer from starvation. Similar to Go, Haskell provides quite limited control over its concurrency runtime. given all the troubles that concurrency causes, it's reasonable to consider if we should avoid concurrency as much as possible. In fact, some of the implementations go pretty far this route. They implement the core protocol logic almost entirely as a completely sequential state machine. The problem is that distributed systems are inherently concurrent, since individual nodes are running largely independently and have to handle events originating from different sources asynchronously. In distributed protocols, there are parts that are fundamentally concurrent, such as handling messages coming from different nodes, and fundamentally sequential parts, such as delivering totally ordered requests. What happens when we try to implement essentially concurrent parts in a sequential manner is that since we cannot simply block in sequential code, we have to multiplex handling of asynchronous events and explicitly maintain and switch contexts. This causes fragmentation of the core protocol logic. Another consequence is that we have to control the flow of events from concurrent sources, and there are basically two possibilities. Either we drop messages, drop events that we cannot immediately handle, or we buffer them. Both add extra complexity, since the code now cannot assume that all events are reliably handled, and in case of buffering, we need to ensure memory bounds. On the other hand, when used appropriately, concurrency can actually help to make our code less coupled, better structured, and can give us higher performance and responsiveness. Nondeterminism is another source of complexity. Distributed systems are inherently non-deterministic due to unpredictable events or the order in which they occur. For example, we cannot know in advance what requests come from external agents like clients. Random numbers, node failures, timeouts are also unpredictable. The same set of messages may arrive at different nodes in different order. And inner working of nodes is another source of implementation-specific non-determinism. For example, due to unspecified order of iteration over unordered collections like sets, scheduling of concurrent tasks, and so on. Distributed protocols to a certain extent are meant to confine this non-determinism within certain constraints. And non-determinism introduces alternative state transitions and expands the state space, thus making reasoning about protocols, implementing and verifying them more complicated due to the state space exposure, and also because it makes reproducing and debugging problems more challenging. So it's useful to control non-determinism or try to eliminate it. To do that, some of the explored code bases implement parts of the protocol as deterministic state machines. This approach is very close to evading concurrency that we considered before and has the same kind of disadvantages. It's interesting how in purely functional programming, ordinary functions are fully deterministic in the mathematical sense, giving the same input they produce the same result. And to express non-deterministic computations, there is the monadic interface, where only I/O actions can cause side effects or produce non-deterministic results, and this is all enforced by the type system. Making code polymorphic in the main I/O-like monad, as in Cardano, allows fully controlling non-determinism by simply choosing the main monad implementation. Controlling non-determinism is especially useful for testing and debugging because it allows us to have reproducible test environments with discrete event simulation. Controlling non-determinism is easier when it's clearly expressed in the implementation, and the type system can help with that. Confining non-determinism within natural boundaries of components can help to reduce complexity and simplify reasoning, whereas simulated execution of unmodified code with controlled non-determinism is a particularly effective testing and debugging technique. Now let's see what communication means to the complexity of distributed protocol implementations. Well, complexity is at the core of distributed systems, since individual nodes need to coordinate with each other in order to behave as a single coherent system. They do so by exchanging peer-to-peer messages. This communication normally happens over some unreliable network medium that can drop data packets or deliver them out of order. Therefore, in general, it's not possible to determine precisely if a remote node has failed or its messages were simply dropped or delayed by the network. Moreover, nodes can also differ in their processing power and experience different traffic load. Therefore, we need to take care of retransmitting the pieces of data that were lost in the network, as well as manage data transmission rate and employ some kind of flow control mechanisms. This contributes to the overall complexity of distributed protocols and their implementation. There are different layers of communication mechanisms. As a transport layer, most of the explored implementations use TLS over TCP. Since establishing a TCP connection and keeping it open is not cheap, they try to keep the number of open connections low and use them over long time. As a consequence, multiple logical substreams often have to be multiplexed over a single transport layer connection. Substrate and Lighthouse use libp2p as their networking stack. libp2p is a versatile, modular, peer-to-peer networking stack. It supports multiple transport mechanisms, encryption schemes, and stream multiplexing. Higher level protocols can be implemented with libp2p on top of reliable, ordered bidirectional binary streams provided by libp2p with transparent encryption and multiplexing. The communication layer in SWI is based on Anemo, a peer-to-peer network library built on top of QUIC. QUIC is a modern higher-level network transport protocol layered over UDP. It has built-in support for encryption and multiplexing and provides reliable, ordered bidirectional streams with built-in flow control or backpressure. QUIC streams are cheap and normally almost instantaneous to open. So there are different levels of communication abstractions. We have low-level transport protocols like UDP or TCP. We have medium-level ones like QUIC, and comprehensive high-level networking stacks like libp2p. There are some useful properties already guaranteed by lower level layers, such as reliable ordered delivery and flow control provided by TCP and QUIC, and I think we should take advantage of those guarantees when implementing higher level layers in order to make them more simple and efficient. In the explored implementations, I found different styles of communication between nodes. The most simple is fire and forget message delivery. It is basically unidirectional sending of messages without waiting for any response. Since there is no acknowledgement, it can only provide best effort delivery and usually gives a no ordering guarantee. Um, the higher level code then needs to handle flow control, retransmission, and establish context for the received messages. It can be expressed with a simple non-blocking interface and also allows sending a message to a group of remote nodes at once, which is a simple form of best effort multicasting. Some implementations additionally provide a non-blocking provide a blocking or a synchronous interface that gives a little bit more control over data flow within the local node to prevent messages being dropped even before they reach the transport layer. Another style of communication is request response, which works by sending a single message to the remote node and expecting a response back, which is essentially the same as the remote procedure call pattern. It's a simple type of session-based communication where sending a request initiates a new session and receiving the response normally terminates the session. Those sessions can terminate abnormally, for example, because of a timeout. Since we expect to receive a response back or an error, it demands blocking or a synchronous interface on the sender side. For that, it provides a context for the response messages by linking them to the corresponding requests. The communication layer treats each individual request-response session independently, and more complex pattern of interaction have to be split into multiple one-shot request-response sessions. Multiple sessions can be initiated concurrently, and the communication layer keeps track of sessions starting, running, and finishing concurrently. A more generic style is session-based communication, which is continuous bidirectional exchange of messages according to some stateful protocol. It's connection-oriented and supports stateful interaction between nodes. Communication sessions in this style represent reliable, ordered bidirectional message streams. It implies blocking or asynchronous interface. This provides a context for the messages being exchanged between nodes and establishes causal relationships between individual messages, which can greatly simplify the protocol implementation. It also takes advantage of the guarantees provided by the stream-based transport layers. It's quite generic and can express many different patterns of interaction. It's well suited for implementing consumer-driven communication, though it cannot directly express multicasting, but multicasting can be implemented on top of session-based communication as a higher level layer. This style can induce some additional latency, but using pipelining techniques we can hide this latency. Finally, there is the gossiping style of communication, which is about publishing and disseminating information in an indirect and random manner. It's a kind of probabilistic broadcasting in a relay network of nodes, where data can propagate from one node to another in multiple hops. It's particularly suitable for sparsely connected networks and can scale very well in large networks. It usually provides the eventual delivery of bounded amount of data with high probability under normal network conditions. It implies a publish-subscribe interface which can be largely stateless and non-blocking. It's often implemented using the advertise request response pattern, where nodes advertise to each other pieces of information that they have and request missing parts from each other and respond to such requests. Though efficient implementations of gossiping can be fairly complicated, since it requires some adaptive topology and using advanced data dissemination techniques. In the Internet Computer blockchain, I found an interesting example of using the gossip style communication, which is called artifact pools. Artifact pools in ICP are structured collections of artifacts or generic pieces of data, and the gossip layer synchronizes artifact pools between different nodes. Then nodes can communicate with each other through those artifact pools by inserting their new artifacts and processing artifacts from other nodes appearing in those pools. The higher level code is responsible for validating artifacts as well as determines the retention and prioritization policies. The most commonly used styles of communication in the explored code bases are the request response and the fire and forget message delivery. As we have seen, different styles have different properties, and this can significantly influence the shape of the code that is built around them. Some styles of communication can be implemented in terms of others, though it doesn't mean that they are completely equivalent, because less expressive mechanisms may have more efficient implementations. So I think it's important to have a range of communication mechanisms with aligned interfaces and clearly defined properties. Apart from communication between nodes, concurrent tasks running within the same node also need to communicate. This internal communication shares some similarity with communication between nodes, providing an interesting perspective which can help us to come up with better abstractions. Some programming models and techniques make this similarity prominent. For example, the actor model communicating sequential processes, remote procedure calls, and so on. The main difference is in the communication medium. While communication between nodes happens through unreliable and slow network, the internal communication uses fast and reliable shared memory. In principle, any piece of shared memory can act as a communication channel which can be established almost instantaneously simply by sharing a memory reference. There is also no need to serialize messages since they can also be simply shared by reference. The request response style can be realized as calling a blocking or asynchronous procedure, the fire and forget style as calling a non-blocking procedure with no return value, and session-based style can be realized, implemented using channels or concurrent queues. And finally, the publish-subscribe design pattern resembles the gossip style and can be implemented, for example, as an event bus or broadcast channel. Um, Similarly to communication between nodes, those communication styles can significantly influence the shape of code built around them. Therefore, it's equally important to have a range of internal communication mechanisms with aligned interfaces and clearly defined properties. For internal communication, channels or concurrent queues are widely used mechanisms. They are fundamental constructs to implement message passing between concurrent components. They can be either buffered or unbuffered, depending on if they can hold items without blocking the sender. Buffered channels can be non-blocking, whereas unbuffered channels are always blocking and act as a rendezvous points. Buffered channels can have different ordering policies, FIFO, LIFO, priority based, or whatever. Buffered channels can be bounded or unbounded depending on if there is a hard limit on the amount of items that they can hold. Unbounded channels usually provide a non-blocking interface for inserting new items. This requires some additional mechanism to prevent accumulating indefinite amount of items, and therefore can make reasoning about the protocol implementation more complicated. Bounded channels usually provide blocking or asynchronous interface, but they can also support non-blocking insertion of new items, in which case they would need to discard some items if there is no more capacity left. Similarly to the ordering policy, there could be different eviction policies. Buffered channels with a single item buffer is an interesting case. For example, one-shot channel in Tokyo and completable future in Java and mvar and tvar in Haskell can also be considered this. It's convenient for communicating a single item between concurrent components. Watch channel in Tokyo, which keeps the last value sent to it, is another example. It's useful for keeping track of a current value updated by another concurrent component. tvars in Haskell are always somewhat similar to watch channels and can be used for the same purpose. Same as channels, publish-subscribe constructs can also be buffered or unbuffered, bounded or unbounded. Another thing that can make distributed protocols complicated is the resilience requirements, because fault-tolerant distributed systems are meant to tolerate within certain limits faults of individual nodes due to crashes, network partitioning, malfunctioning, or even malicious behavior. There are two broad classes of fault-tolerant systems. One is crash fault-tolerant systems that can only withstand node crashes and network partitioning. For example, Apache Kafka and Zookeeper belong to this class. Another is Byzantine fault-tolerant systems that can, in addition to that, withstand arbitrary or even malicious behavior over a fraction of nodes, and typically public blockchains belong to this class. However, those theoretical guarantees only hold if the implementation ensures that the required assumptions also hold. And this can be pretty challenging in Byzantine fault-tolerant systems that operate in adversarial environments, because nodes there can be subject to various attacks, such as denial of service attacks, and fairness between peers would be another concern in those environments. There are basically two sides of the issue. One is effectively preventing faulty nodes from compromising the whole system, and another is safely and efficiently recovering the nodes that has failed in order to bring them back to the system. So many implementations maintain some kind of reputation metrics for their remote peers and apply rate limiting. Such peer reputation is usually based on the observable behavior of the remote peer, such as protocol violations, timeouts, and performance. In order to use that effectively, there should be a clear path for propagating information about any detected protocol violations and anomalies. Then the communication layer can use that and disconnect from the remote peers whose reputation drops below a certain threshold, and further reject inbound connections from those offending peers. It's worth mentioning here the Cardano's threat-aware design approach, which is based on detecting and reacting upon protocol violations as early as possible, which is accompanied with using stateful consumer-driven communication schemes. As mentioned earlier, failed nodes should be able to effectively restore and safely rejoin the system. To achieve that, some parts of the protocol state is normally persisted in a stable storage, which is usually implemented as a write-ahead log. This allows nodes to safely restore and continue participating in the protocol. Persistency is also required to support recovery from a massive system crash, that is the durability property. Optimization can also make things more complicated. Unfortunately, simplistic designs and implementations tend to have rather poor performance, whereas we want our systems to scale well as to provide high throughput and low latency. We can improve performance by optimizing both at protocol and implementation levels, though this often means adding more complexity and making protocols harder to reason about and implement. Optimizing at the protocol level often requires using more complex communication patterns and topologies. For example, to improve responsiveness, we can do protocol phase pipelining, where a single message participates in multiple protocol phases at once, or employ speculative execution techniques. To reduce communication overhead, we can do batching or use advanced cryptography like threshold signatures. It can also help to use advanced data structures like DAGs. At the implementation level, there are such well-known optimization techniques as on-demand execution, caching, and so on. Communication contributes a lot to the overall overhead in distributed systems, and therefore is a clear target for optimization. For example, we can try to hide high network latency by using peer-to-peer protocol pipelining, where we send requests in advance without necessarily first waiting for a response. Transport protocols like TCP tend to perform better under steady data flow, and we need to take that into account. Multiplexing logical communication streams can help to consume less system resources, though we need to be careful in order to minimize the head-of-line blocking effects and perhaps transmit large pieces of data in chunks. It can also make sense to have specialized communication mechanisms for particular purposes, for example, to do state synchronization in a blockchain system. To get maximum performance, we might want to do some fine-tuning and try to optimize interaction between components. We can do that with prioritization and flexible policies applied to certain concurrent tasks or communication paths, to some individual messages or kinds of messages. This kind of optimization requires really deep understanding of the protocol and its inner workings. Some expensive low-level operations can also be a hidden cause of suboptimal performance, for example, spawning threads, blocking on locks, copying data, and so on. Here, execution pools can help to avoid the overhead of operating system threads for executing short-lived concurrent tasks. We can use non-blocking algorithms to avoid unnecessary suspension of thread execution, and zero copy techniques can help to eliminate excessive copying of data. To support optimizations, we need a flexible enough structure of code so that we can apply optimizations not only within components, but also sometimes crossing the borders of modularity. We need flexible and composable primitives and interfaces that are designed for optimization if we want to fully realize the potential of distributed systems in practice. Now we switch gears and get to another major aspect of implementing distributed protocols, which is correctness. Correctness is absolutely essential for distributed fault-tolerant protocols and their implementations, since they play a critical role in ensuring consistency and reliability of the whole system. There are formal verification methods that allow confirming protocol correctness with mathematical rigorousness. They require that protocols are described precisely with a formal specification. When we implement protocols, there is often some discrepancy between the protocol specification and the code because the notations used there are quite different. This could be a potential source of errors. To examine correctness of software, there is an established practice called testing, which normally happens at different levels, like unit testing, integration testing, and system testing. Modularity here supports more effective unit testing and simplifies integration testing. To facilitate testing, some implementations introduce dedicated interfaces and hooks for testing purposes. In Aptos and SUI, I found an interesting mechanism called fail points that allow injecting errors at runtime during testing. In Algorand, there are pre and post condition checks that happen at different levels of the hierarchical state machine implementing the consensus protocol. Diagnostic logging or tracing can also be useful for testing, for example, to check some complex invariants in property-based testing. Deterministic discrete event simulation is a very powerful technique that can be used for randomized but reproducible testing. I found it used in SUI, Apache Kafka, and Cardano. It works by running the code within a special runtime that ensures deterministic, randomized execution of concurrent code and provides a faster than real-time simulation of time delays. It can run an entire network in a single process with the network simulated. It usually requires that the code is generic over the sources of local time and randomness, but can also rely on code instrumentation techniques. Most importantly, it allows running precisely the same code in the simulator for testing as in production. Uh, Static compile time checks can greatly help to ensure correctness of our code even without runtime testing. Uh, for instance, type safety features can make the code simply safe by construction. It's worth mentioning session types used in Cardano. In session types, peer-to-peer protocols are described as state machine encoded directly in types, and where transitions between states correspond to messages exchanged between the peers. The protocol state determines which messages can be sent or must be accepted, all at the type level. It greatly simplifies protocol implementation and allows to detect protocol violations early. Remarkably, it makes the protocols deadlock-free by construction. Though using more advanced type-level programming techniques may allow achieving impressive levels of type safety, but they can make code significantly harder to implement, understand, and maintain. The next major aspect I wanted to talk about is resource utilization. It's important because computing resources available to the nodes are fundamentally bounded. We have limited computational power, memory, storage, network bandwidth, and also there are some limits on system resources like threads, open network connections, file handles, and so on. So proper resource management is indispensable in long-running systems, and we must prevent resource leaks and ensure fair and efficient utilization of available resources. Some resources must be explicitly released when they are no longer needed. For example, allocated memory, open file handles, network connections, concurrent tasks, and threads. And failing to release resources in time is known as a resource leak. Relying on explicit releasing of acquired resources is error prone, and there are some automatic resource management techniques based on lifetimes and lexical scopes which are more robust. But sometimes strict lexical scoping becomes inappropriate. In those cases, we might need to resort to managing resources in a more explicit way within the scope. But we should have a fallback mechanism that keeps track of resources and ensures they are properly released whenever we leave the scope. Concurrency often makes resource management more challenging. First of all, concurrent tasks running in background is also a kind of resource that needs to be released. Moreover, when a concurrent task is terminated, for example, with asynchronous cancellation, we need to ensure that any other resources acquired by that task are properly released. Here, the structured concurrency approach can help by organizing concurrent tasks into a structured hierarchy with well-defined scopes and lifetimes. Individual parts of a distributed system may operate at different pace, and we often use pipelining techniques when communicating with remote nodes. To compensate for the delays and variability in throughput, there is very often some form of buffering, for example, buffered channels, send-receive queues, pending request trackers, out-of-context buffers, just to name a few. Under certain conditions, the amount of buffered state tends to grow, and there should be some mechanism that prevents this buffered state to grow out of bound. For example, back pressure, rate limiting, item expiration and eviction policies, and so on. In adversarial environments, denial of service attacks through resource exhaustion is a serious concern. In order to effectively defend against those attacks, they should be prohibitively expensive for the attacker compared to the amount of resources consumed from the honest nodes. Here, early detection of protocol violations and consumer-driven data flow, as in Cardano, can greatly help. It can also be useful to track resource expenditure caused by remote nodes, as in Avalanche, and apply fair throttling to communication channels. Now let's jump to another major aspect, maintainability. It's challenging to maintain long-running complex distributed systems, especially when nodes may be controlled by different independent entities or in publicly available deployments where nodes are subject to malicious attacks. It all begins with setting up the system, and some protocols may require specific bootstrapping procedures or rely on certain assumptions for the setup phase. So it's important to make those requirements and assumptions clear. Sometime after the system is up and running, we may need to upgrade individual nodes with newer versions of the protocol implementation without disrupting the system. And this requires that the implementations are backward and forward compatible. Sometimes node may stop or crash, and we need to be able to recover and rejoin those nodes safely and efficiently. When more nodes crash than the system can handle, we may want to be able to recover from such a massive system crash, and in order to do that, the system should provide the durability property. So we need to design and implement protocols with clear recovery procedures as well. Distributed systems administrators need some mechanisms and tools for monitoring individual nodes to analyze the system and promptly detect anomalies. Same mechanisms can also be effective for analyzing, diagnosing issues, and identifying bugs. There are common observability techniques that can be used for that purpose, like logging, tracing, and collecting metrics. Most of the explored code bases use those techniques based on OpenTelemetry and Prometheus, which are popular open source monitoring solutions. Let's look at those techniques one by one. First, diagnostic logging records chronological textual messages that capture important events during execution. Log messages are traditionally assigned a severity level that allows disabling messages below a certain level, for example, omitting debug messages in production. Log messages can support addition of some structured data like key value context fields. Diagnostic loggers can also be organized hierarchically, reflecting the structure of components. Tracing is similar to logging, but more focused on providing a detailed view on the flow of execution. Tracing events are primarily structured rather than textual and reflect causal relationships. In particular, distributed tracing keeps track of events caused by processing individual logical operations such as user requests as they happen across the distributed system. There, a distributed trace is associated with a single logical operation and consists of spans that represent particular activities within the operation. Spans are linked together with causal relationships and normally contain structured data about the activity and timing information. And finally, metrics are numeric measurements that describe the system's behavior over time. They are typically collected and aggregated at regular time intervals and usually include some various types of information like CPU and memory utilization, latency, error rates, throughput, queue lengths, whatever. There are different kinds of metrics, and the most commonly used ones are the counter, which is a cumulative metric that monotonically increases over time. There is the gauge, which represents the current value of some measurement, and the histogram, which records sampled observations in a statistical representation. Observability is a cross-cutting concern because it's needed in almost every component. Most implementations define abstract interfaces for those mechanisms and require them as dependency in their components. Some use code instrumentation techniques. Cardano uses an interesting approach called contravariant tracing. In contravariant tracing, domain-specific event values are provided to domain-agnostic processors. It allows domain-agnostic tracers to be adapted and used as a domain-specific tracer inside components. It encourages using dedicated domain-specific event types rather than some textual encoding. It can also be used to collect metrics. Sometimes detailed logging and tracing can add significant overhead, and when it's undesired, logging and tracing can be sampled based on some predetermined sampling rate or criteria. Contravariant tracing incurs zero runtime cost when compiled with tracing disabled, and it's even possible when a tracer ignores only certain types of events. We are finally at the last major aspect, flexibility. Flexibility is a property of code that allows to adapt it to changing requirements without extensive restructuring. It's crucial for adoption, reuse, and evolution of code. It's important to keep in mind that every single assumption or requirement that we put on how the code can be used constrains its flexibility. I find the explored code bases are quite specific. They implement particular protocols or serve specific purposes rather than trying to address fundamental needs for implementing distributed protocols in general. This is a common approach to building software, but it tends to limit flexibility of the code. Highly modular and composable code is also more flexible. So clear separation of concerns, abstract interfaces and dependency inversion help to make the components more interchangeable and the code easier to modify and extend. Designing components as generic and configurable, for example, using generic programming techniques like parametric polymorphism, helps to make components more adaptable to be used in different contexts without modification. The ability to seamlessly integrate into larger systems is required for adoption and reuse of protocol implementations, because larger systems may opt for different programming languages and runtime environments. Therefore, it's important to support interfacing with other languages and impose minimal runtime requirements. The Rust language seems to be a good choice to implement robust software for integrating into other languages and environments due to its rich language features, zero cost abstractions, predictable performance, safe memory management without using a garbage collector, and the ability to use custom concurrency runtimes. I think that designing for flexibility should be a deliberate choice from the beginning. So we've talked about the aspect of complexity in implementing distributed protocols and the roles of modularity, concurrency, non-determinism, communication, resilience, and optimization in that context. Then we've looked at the aspects of correctness, resource utilization, maintainability, and flexibility. Now let's make some conclusions. I learned a lot while exploring the protocol implementations. Now I have much deeper understanding of what's important for a protocol implementation in practice and what are the typical challenges there. I saw different approaches in use and also discovered some interesting ideas and techniques. Though I find it quite unsatisfactory the ways the protocols are implemented. Even for an engineer experienced in implementing this kind of protocols, it was fairly hard to comprehend and follow those code bases. I can imagine how much effort and pain it took to first make them work as well as to improve them later. Most of the time it was hard to follow the main protocol and see the causal dependencies and logical connections in the code that was presumably structured focusing on the operational aspects, which is fragmented, entangled, and cluttered. Uh, Most often the communication mechanisms used there are rather simplistic without taking advantage of reliable and orderly delivery guarantees provided by the transport layer. Um, Concurrency and synchronization are often expressed explicitly in terms of low-level mechanisms, uh, or the implementations try to avoid concurrency in favor of sequential state machines, making the protocol logic fragmented across the code base and shifting the focus from semantics towards mechanics. Here and there are invasive ad hoc optimizations, patches, and cross-cutting concerns modeling the code. I find most of the code bases are not modular enough, have somewhat unclear structure, excessive coupling, and abandoned in mutable state. Uh, some implementations also use sophisticated techniques and have very little, and there is often very little inline documentation, which makes understanding the code very hard. I'm afraid it's mostly hard to judge if the implementations actually correspond to the original protocol closely enough and provide the required guarantees even under most unfavorable conditions. The code doesn't appear anything like formal specification, and there is always a possibility of such nasty bugs as race conditions, deadlocks, resource starvation, data races, and so on. Non-determinism is often unconstrained, and there is abundance of non-local operations, which makes rigorous test-based verification practically infeasible. Only a few of the implementations support reproducible testing of unmodified code. I was also not sure how those implementations would behave under certain high load conditions, for example, under a denial of service attack. Because protocol violations are not always optimally detected at early stages, and many implementations lack mechanisms to propagate this information about the detected anomalies appropriately and take the corresponding measures. The majority of the implementations employ the push style of communication and forego the flow control mechanisms provided by the transport layers. That allows the remote nodes to send arbitrary amounts of data that the receiving node would have to deal with. Embarrassingly often there are unbounded buffers and queues, and the mechanisms that could prevent from unbounded growth of state are not clear. There is often unreliable hand-coded resource management that could cause resource leaks, including the concurrent tasks dangling in background. As of observability, most implementations simply do some logging with context fields and collect metrics, and that may not provide enough details and context for effective debugging and analyzing of the protocol execution. All of the implementations are quite specific to particular protocols, execution environments, and use cases. There is rather coarse modularity, and most components are not reusable nor composable, and tight coupling is also not rare. I think we can do better. We should not waste our efforts reinventing the wheel again and again and repeating each other's mistakes. Builders better focus on the functionality that is specific to their solutions without having to figure out how to approach implementing those critical distributed protocols. So we need a framework to solve the problem of implementing distributed protocols once and for all, with structured yet flexible enough approach, guiding away from incidental complexity, focusing on understandability, fine modularity, and composability, with generic and configurable components supporting local reasoning about their implementation, providing safe, easy, structured and composable concurrency and communication abstractions. A framework that is serious about correctness and resilience against unfavorable conditions, catering for maintenance needs with great observability and diagnostic mechanisms, allowing for various optimizations and delivering good performance. The Replica.io project is about creating such a framework, and for the next steps I defined the following key areas to focus on. The first one is simplicity, which is making protocol implementations well structured and understandable. The second one is flexibility, which is keeping the framework adaptable, widely applicable and evolvable. The third one is reliability, which is ensuring that protocol correctness is verifiable and the implementation is resilient. Another one is efficiency, which is allowing for various optimizations and delivering good performance. And the last one is maintainability, which is catering for maintenance needs and providing great diagnostic mechanisms. Obviously, it's not realistic to achieve this all at once, so initially the primary focus will be on simplicity, flexibility and reliability, but without neglecting the remaining aspects. Of particular interest are composable structure and notation for concurrency and communication mechanisms, as well as ways to control nondeterminism. So the next step will be to continue exploring the state of the art, first by selecting and examining some existing frameworks for developing distributed protocols, and then exploring some potentially related concepts, approaches and techniques that are worth looking into. After that, it will be time to come up with the key ideas for the core principles of designing and implementing components within the framework. That's milestone M0.1. Then those ideas will be developed into clearly formulated concepts in milestone M0.2. Their feasibility will be verified with code in milestone 0.3. Then the prototype, MVP and production versions of the framework will be developed and released in milestones M1, 2 and 3. Though it doesn't mean that the exploration, ideation and prototyping will not take place at later stages, the milestones are there to reflect the overall maturity of the framework. So the framework will be continuously evolving and expanding until it becomes a de facto standard, providing a growing collection of distributed replication mechanisms that are ready to use or can be mixed and matched as needed. If you would like to learn more about the project, please go and visit its website. There you'll find some links where you can follow the project and participate. You'll find the link to the website in the description of this video. You can also support further development of the project by sponsoring it on GitHub. If that does not work for you, please drop an email and we'll find a solution. That's all for now. Thanks for your interest.